Oh, yeah. So as I had mentioned, one of the announcements, there's not that much left to cover. Like definitely I'll be done with it on Monday, although I expect that more or less almost everything will be done today. So yeah, what we can do on Tuesday is like more like kind of like some sort of extended office hours or review. So you can come if you want to ask me something about that. About like if you're stuck with a specific topic, we can go over it. The same for I mean Monday. I'm guessing we may have like some time. Like I don't think I would spend the 2 hours like covering what I need to cover. So also on Monday, if you have specific questions that you want to ask me about, we can discuss that as well. So just like keep that in mind, because I imagine you probably will start studying over the weekend for the final. So um, yeah, after today, like not after today, the only thing that you wouldn't be able to do on the for the final is like the stuff about conic sections. That's like I think the only topic I would have to cover on Monday. But that's relatively easy. No, it's just the assignment that I don't know if you remember that I had created this assignment that was due. When was it due? Like Saturday, maybe or Friday. So it's just like in instead of that assignment. Um, so just to try to um so there's an assignment on Grayscope. I believe I had created like an announcement about it. Oops. Yes, sorry. Saturday night, thanks. So yeah, that and I think that would be like the last assignment. I mean, like next week obviously wouldn't I don't know if there was I mean I guess there was nothing scheduled anyways on the syllabus, but like it wouldn't make a lot of sense to us. So yeah, that assignment is the last assignment that you have to like upload um on Canvas. Oh no, I'm feeling better. It's just like I had to take a flight, and sometimes like in the airports, like you get dizzy, and so. But thanks. So yeah, as I was saying, the assignment is just. I mean, the assignment counts for the quiz, basically. So there's no quiz today. Just give me a second to. Okay, now fine. So yeah, today. What is the lecture for today? Today is lecture 17. So okay. So the first thing I have to tell you, there are two things like, especially that I want to go over for today. So if you remember what we were doing last time is that if like so last time you could have you can have a basis for a vector space. Let's call this basis I don't know how many vectors you require, so let's call them UK. So let's say you have k vectors for the vector space. For a vector space V. So the the point is that these bases, if you think about the vectors, their angles may not be 90 degrees. So the vectors, like if you think about the vectors, you can think of vectors literally as like just take some pens and like for example here there are like three vectors, right? And if you look at what I'm holding, they don't hopefully they don't look perpendicular, right? Like but this actually you could think of this as some sort of basis. If there are three vectors, it would be for a vector space of dimension 3. So they are like a basis, but they're not like the vectors are not orthogonal or perpendicular. So what the Gram-Schmidt method does is kind of like fixes them a little bit so that they become mutually perpendicular. So the idea of Gram-Schmidt, so the process of Gram-Schmidt, like What it does is to it produces a basis which is perpendicular out of your initial basis. So it creates an orthogonal basis from the one you started with. Okay, you can call these new bases like V1 up to Vk. So let's call this basis. So just to remind you, like how it's kind of like, again, it's not so clear why it works because of the way I decided to do it. Like there's like a way to do it which is a little bit more geometric. It's just that it is like a way more complicated formula. But the way I told you to do it is like it's very easy actually. For example, if you, I don't know if you remember, like if the basis had been these two vectors, then the thing that you have to do is like arrange them into a matrix where the vectors becomes rows. So that's the only thing you have to remember. The direct vectors should be written as rows in this matrix. Okay. I should put this should be this should say transpose. It looks like a square. Okay, and then so you get this matrix whose rows are the basis vectors, and then you do A transpose that gives you a new matrix, and you reduce A transpose together with the matrix A until the stuff on the left-hand side becomes upper triangular. So the goal is always to just get to an upper triangular matrix on this side, which is a lot faster than trying to reach the identity. So this method is, I mean, this procedure is faster than just like when we were trying to find like the identity matrix, for example. The thing is like you just like do the row operations on both sides simultaneously. So as you get this one to upper triangular, this one starts getting modified, and so what the algorithm says is that like what once you get this to upper triangular, whatever vectors you have here, they are the orthogonal basis. So for example, if you look at these vectors, what does it mean to be orthogonal? It means that their dot product is zero because having perpendicular vectors is for the means that the dot product has to be zero. So if you do the dot product between the green vector and the blue vector, you'll see that you get zero. So that means that they're perpendicular. And then the other one which we had done, let's see, yeah. Yeah, and the other one we had done was like this other vector space. Let's say that this vector space had this basis, okay? So again, you arrange it as rows. Do the A transpose thing first to see what this matrix gives you. And you just start trying to reduce this to upper triangular. So you want it to look like this. So we get to this stage. And whatever ended up happening to these vectors, they become the orthogonal basis for the vector space. So this would be the first vector, the second vector, the third vector. And if you look, like, again, it is the good thing about this problem is that you can always check whether you made a mistake because you can literally always compute the dot products to see whether they're zero. And the dot products are relatively easy to know, to do. So if you do the dot product of this with this, you get zero. And then the dot product of this with this also should give you zero. And then the dot product of this with this should also give you zero. So no matter which two vectors you take out of these bases, they will always be zero. Their dot products will always be zero. So that means that you kind of like straighten out the vectors to make them perpendicular. Okay. So that's almost all that we need. You'll see in a second why it is useful to have orthogonal vectors as a basis. The only thing that's left is that not only is useful to have them of perpendiculars being perpendicular, but also it's convenient to have them being of length 1. Okay, so let me just write that down. And that's all. So like the only thing that we have to do is fix their lengths at this point. So let me give you this as a definition. A basis for a vector space is orthonormal. Orthonormal. That's how it's called. So orthonormal basis if there's just two things that need to happen. Every vector in the base, the vectors of the basis must be mutually perpendicular. Okay. And the second condition, or mutually orthogonal. Again, perpendicular means the same as orthogonal. They're synonyms. And the second condition is that each vector in the basis must have length 1. That a vector of length 1 is usually called a unit vector. So it's kind of they're mutually perpendicular and each vector has length 1. So that's all that it needs. So besides like the stuff that orthogonal basis was just condition 1, and orthonormal basis adds condition 2. So let me write that as a remark. Is that making sense? And orthonormal basis adds condition 2. So, but the thing is that condition 2 is very, very easy to achieve once you have found the orthogonal basis. So how can you find an orthonormal basis? Okay. So just to make a picture like of the situation, like imagine that you have a vector. Imagine that you have this vector, which is remember like a vector, like I had this notation for the length of a vector, which is 3. Let's say that this vector has length 3. So this is like an example. This notation just as this notation looks like the absolute value notation, but it's just like it just means the length or norm of the vector. Okay, so imagine that you had a vector which has length 3, right? And you wanted a vector of length 1 in the same direction as this vector that you have here. So let me see if I can. Maybe it has to look a little bit smaller. So I want like a vector that's kind of parallel to this one, right? So these two are parallel, but this one will have length 1. So how could I get this vector out of the original vector? Well, you kind of just like, if this one has length 3, this one has to be like a third of the original vector, right? So the idea is that this vector should just be like the original 1 divided by 3. So this would be like, let's call it like W over 3, which is W over its length. Okay, this will be a vector parallel to W, but of length 1 now. Is that making sense? So like the point here is that if you have a vector, you can always create like a unit vector just by dividing that vector by its length. I may have said that, but it would have been a long time ago. So, but it's like, it's like a very plausible thing to imagine. So that's more or less what we would do to get like the orthonormal basis. So we will find the orthogonal basis using this Gram-Schmidt thing that I told you. And then at the end of the process, you just divide each of the vectors that you got by their length, and that will make them orthonormal. So how do you find like an orthonormal basis? So first find a base, an orthogonal basis using this Gram-Schmidt. Find an orthogonal basis. And then divide each vector that you got from step one by its length, and that will give you the orthonormal basis. Divide each vector you got in step one and this will be these will be the orthonormal basis. Okay. So I'm about to do that for the two examples that for the two orthogonal bases we had found that I showed you a couple minutes ago that we had found last time on Tuesday, I guess. But again, the finding the orthonormal basis once you have the orthogonal basis is like very, very straightforward. It's just like computing like the length using Pythagoras theorem. So let me show you how this looks like in these two examples. So in example one, or let's call this example A, we had this a vector space. So these are from before. We had this vector space V with bases 1, 0, 1, 0, 1, 1, right? After doing Gram-Schmidt, the orthogonal basis was we found was 1, 0, 1 minus 1 half, 1 minus 1 half. Hopefully you remember this. Okay. So now what we have to find their length. Okay, so what is the length? Let me in fact write them with different colors so that we can isolate them. Okay, so this is already orthogonal. Oh, these two vectors are already at 90 degrees. So now we have to find the length of each vector. So what is the length of the first one? Let's call this, let's call this, let's not give this a specific name. So let me just put like the absolute values notation just to make you comfortable with this notation. So if you put like kind of like, this looks like absolute values. If you put like absolute values inside, like next to a vector, like what that means is just the length of the vector. So this is like a notation for the length. The length is just a Pythagoras theorem. So if you remember, like the Pythagoras theorem is that the square root of the sum of the squares of each entry. So you take the square, it's always the same. So you square each entry, so it's 1 squared plus 0 squared plus 1 squared. Okay, and the length is the square root of that. So this gives you the square root of 2 in this case. So once you have that, or like the unit vector is just 1, 0, 1 divided by its length, which is root of 2. And that looks a little bit ugly to write it like that. So you can put like the root of 2 inside each entry. So you get this. So this is a unit vector corresponding to 1, 0, 1. Is that making sense? So it's literally just dividing by the length. In this case, the length was root of 2. So you have to divide. It's essentially dividing each entry by root of 2. So that's how you get that. And the thing about doing that is that since you're just like the point of dividing by the length is like the most you're doing with to the vector is kind of rescaling it. So that since it's just like a stretching factor, it will continue to be perpendicular to the other vectors. So this vector, if you don't have to check it, but if you did the dot product between this vector and the red one, it will still continue to be 0 because you just dilated the vector, so you didn't change the angle this vector had with the other vectors in your problem. Okay, so that's like the cool thing about rescaling, that it doesn't affect like the answers in that sense. Like it doesn't mess up the perpendicularity of the vectors. That's what I mean. And is that okay? Are there any questions about this? Okay. Now, let's do the same for the red one. So what is the length of the red vector? It is the square root, again, Pythagoras theorem, it says is the square root of the squares of each entry. So you have to square each entry and then add them together and take the square root of that. So this gives you 1/4 plus 1 plus 1/4. This is 1/2 plus 1. I mean, if you add them together, I mean, this will give you what? 3/2, I guess. You can. Okay, so the length of this vector is root of 3/2. And so the unit vector is just the vector you started with divided by its length. I mean, here there are different ways to write it, but because this doesn't look too nice, you could put it like, I mean, 3/2 is 1.5, so you could just so that, I mean, there are different ways to, let me put it like root of 2.5 because otherwise. Like I'm not like once you have the orthonormal basis, that I mean that's the important thing. Like there are different ways to rewrite it because like you for example could also have left. I mean it's also fine to leave the answer this way. It's just that it looks a little bit messy. If you put it like this, it looks a little bit better. But I mean, there again, like maybe you don't like to. You could have kept it as a fraction, like root of 3/2 and things like that. So there's slightly different ways to. This looks like 15. Like let me put 1.5. there's slightly different ways to do it, to write this out, but like the point is that now the orthonormal basis would be these two vectors. So the orthonormal basis are those two vectors that we found. Is that making sense? So again, if you were to do, like, the point is that each of these vectors would have length 1. Each of these vectors has length 1, and each of these vectors, and the vectors are mutually perpendicular. So that is the point of finding the orthonormal basis. Let me do it for the other. Let me do it for the other example we had found last time. Let me find the orthonormal basis in that case. Let's see. What was the other example we did? Second example we had done. So we had this vector space with bases. The bases had vectors, if I'm not mistaken, 0, 0, 1, 0, 1, minus 2, 3, 0, 1. And then 1, 1, 1, 5. So after you do Gram-Schmidt, you find, and again, let me put this like in different colors. So like what we had found last time was 0, 1, 0, 1. That still remains the same. Then minus 2, 1, 0, minus 1. And the last one we found was minus 1, minus 1, 1, 1. So what is the length of this one? The length equals 0 squared plus 1 squared plus 0 squared plus 1 squared. So again, the Pythagoras theorem is always, no matter how many entries the vector has, you always square each entry, add those together, and take their square root. So it could have 10,000 entries, like it is the same process. So that just gives you, this one is still the square root of 2. What is the length in this case? The length is, when you score the first one, you get 4 plus 1 plus 0 plus 1. Right, and that is what? That is square root of 6, right? And what happens when you square the last one? The length, again, well, these are all ones, so it's once, I mean, minus 1 or 1 squares to 1. So it's 1, oops, it's 1 plus 1 plus 1 plus 1. Okay, and that gives you square root of 4, which is 2. So the unit vector, what are the unit vectors? The unit vectors are each vector divided by its length. So the first one would give you, you have to divide each entry of the vector by root of 2. So it gives you 0, 1 over root of 2, 0, 1 over root of 2. Then you have to divide each entry of this second vector by root of 6. So it's minus 2 over root of 6, 1 over root of 6, 0, minus 1 over root of 6. And you have to divide each entry of the last vector by 2. So it's minus 1/2, minus 1/2, 1/2, 1/2. And again, if you were to do the dot products between the new vectors, they continue to be zero because they're just rescaled versions of the original ones, which were already orthogonal. So this is like the orthonormal basis for the vector space.
Professor, could you show me how did you get the um on the vectors, how did you get -2, 1, 0, and -1?
This one, these numbers?
Yeah. Yes.
So it is from the example that we had done. Let's see, where do I have it? Okay, it is an example we have done last time. So in that example, like, I
Oh,
gave
yeah.
you.
Oh, okay.
Yeah,
Okay,
yeah. So
then.
it's otherwise because I mean, usually like the way that I'll ask you this question is like I'll give you a basis, right? I'll first ask. I mean, I'll just ask you to find like an orthonormal basis for the vector space. The way you should do it is like you first find like an orthogonal basis using this method. Once you have the orthogonal basis, then you rescale them. But so yeah, I'm kind of doing like the last step of the. It's like a two-step process. I'm doing the second step just because we had like the answers from before for the first step. But yeah, like the way I would ask it is like I'll give you a vector. I'll tell you here's a vector space. It has this basis, right? Find an orthonormal basis. Find an orthonormal basis for it. So first you find the orthogonal basis, like as you using this stuff, and once you have that, you rescale them, and then you're done.
Okay.
Is that make sense?
Thank you.
Sure.
Yeah.
And again, like that, it's not too bad. Like usually you shouldn't be worried. You'll see a lot of square roots in these answers. That makes sense because you're using Pythagoras theorem that involves a square root. So it's kind of so it is not uncommon to see that. Now let me tell you why we're finding an orthonormal basis, and then I will show you like an application that we can do with it. So why why do we care about getting an orthonormal basis? The main reason is that it gives you like it gives you like a direct formula for writing a vector as a linear combination in terms of the basis. So it gives you a way, a simple formula. Let me write it like that. A simple formula for writing a vector as a linear combination of the basis vectors. So what do I mean by that? Let's say let's do it in a concrete example. So let's say that you had here's an example. Let's say that V, and then I'll give you the general formula. Let's say that V has like it's a vector space, right? Of dimension 3. So that means that it like the basis that it can like the any basis that you find for V has three so it has three basis vectors. Like so any basis has three vectors. Let's just say it that way. So what does that now how does that look like? Let's say that you have like an orthonormal basis, because now we know that we can always find them. Like the cool thing about this process is that you can start with an arbitrary basis in the world that you like. You start with your favorite basis, you fix it by making it orthogonal, and then you rescale it and you have something orthonormal. So what that is saying is that any vector space always has like an orthonormal basis, because you can always start from like an arbitrary one and correct it. So let's say that you have like an orthonormal basis for this vector space. And by the way, there's not like a unique choice of orthonormal basis. There's still like infinitely many choices, but it is more restrictive than just having like a basis. Because it's the vectors satisfy more conditions. So you still have like so you would have like an orthonormal basis. Let's call this like these vectors v1, v2, v3. So how does that look like? I mean, let's just try to draw like three mutually perpendicular vectors in space. Like maybe it looks like this. Here's v1. Maybe v2 looks like this. Here's v2. And v3, you kind of have to try to draw something perpendicular to both of each of them. Okay, let's see, something like this. Okay, I mean, it's always difficult to draw these things like because it's on the piece of paper, but you know, like, think of this angle as being 90 degrees, this angle as being 90 degrees, and this other angle as being 90 degrees. So like an orthonormal basis, if it like the basis is dimension 3, like it kind of looks like that. And then and like here I'm trying to, you know, make the vectors have the same length because each now has length 1. Okay. But now what is what's the point of this? Let me. The point of this is that if you choose any other vector v in the vector space, right? Any other vector is a linear combination of the basis vectors. That's the whole point of a basis. So any other vector v is a linear combination of the basis. So that means that v is like a constant. We can call it like c1. I mean, it doesn't matter if you want to call this c1 or x, but let's call it c1. It can be too confusing otherwise. It's like a constant times the first vector plus a second constant times the second vector plus a third constant times the third vector, right? Like the point of a linear combination. The point of a linear combination is just like a regular sum, but before taking the sum, you're allowed to rescale each vector. So you can write it as okay, but up to now, here's the thing. Up to this point, like there was not like a very good way of finding these coefficients. Like you more or less had to solve like a system of equations. I don't know if you remember. If you wanted to find like a vector, it's a linear combination of vectors, you kind of had to set it up as a system of equations. So you always had to solve like a system of equations to find these coefficients C1, C2, C3. So that's fine, but you know, like solving a system of equations can be sometimes a little bit more inefficient. But in this case, when the basis is orthonormal, there is a faster way to find the coefficients. So how can you find them? Let's do the following. Let's take this equation. Okay, this is like an equation between vectors. So I will take the dot product on both sides of this equation with respect to v1. So let me show you what I mean. So I'm going to do v1 dot v. So I'm going to take the dot product with respect to v1. So that's going to be v1 dot just give me a second. So I'm going to take v1 with the dot product of okay, so like you know, I kind of like you know, I dotted but both sides of the equation with v1. You're allowed to do that because you had a vector here and a vector here, so both sides can be you can take the dot product of both sides with respect to V1. Now, what is this? What is the right-hand side? I don't know what it is because I don't know in particular what the vectors are, but the left side. I don't, the left side, there's not much I can simplify this with, but I can simplify the right-hand side because I can use the distributive property of the dot product. So that's going to give you like the following. If you distribute the dot product, it will give you like C1, V1 dot V1, plus C2, V1 dot V2, and then plus C3, V1 dot V3. Is that making sense? So if you use the distributive property of the dot product, then you can just the right hand side you can compute instead this dot product. But the point is that now we do have because the basis is orthonormal, we can actually say a little bit about what these dot products are. So for example, what is this? What is this dot product? Anyone can take a guess? What's the dot product of V1 with V2? That is just zero because the vectors in the orthonormal basis are perpendicular. So this dot product is zero because they are perpendicular, and for the same reasons, this dot product is zero as well. Now, the one that's a little bit more interesting is maybe what is the dot product of this first dot product, but if you go back, um, sorry, just to go back to show you where I show you this. Like if you go at the beginning of the dot product that we had discussed before, like I had told you that the vector dot product of a vector with itself is a length square. So this is actually the length. This is actually the length of V1 squared, but it is an orthonormal basis, so the length square is just 1 squared, so you just get 1. So like the surprising thing here is that you are getting a formula for C1. C1 is just the dot product between V1 and V.
Professor, but how did you know V1, vector V1 times V2 goes to 0?
I said like we are assuming by hypothesis that they were like an orthonormal basis. So that means that their angles is 90 degrees between the vectors. It's just that if the vector between if the angle between the two vectors is 90 degrees, the dot product is always zero. It's kind of like an equivalent way to say the vectors are perpendicular. The vectors are perpendicular only if their dot product is zero, or if and only if, basically. It's a key property of the dot product. In fact, like that if you take the dot product and it gives you zero, then the vectors were at 90 degrees. And so it goes both ways, basically.
Okay, gotcha. Thank you.
Sure. And so, but the cool thing, the important thing here is like to just notice, like you have like a very clean formula for the coefficient. It's just the dot product between the vector you started with and the corresponding basis vector. Let's see. And like, there's nothing special about having taken the dot product with V1. I could have done the same for C2 and C3. So in fact, let me write it here. Like what would be C2 and C3? It is the same. It's just that you change the vector you're taking the dot product with. So for C2, For C2, you would use the red vector, so it would be V2 dot V. And for C3, you use V3. So the point is that whenever you have an orthonormal basis, the coefficients of the linear combination are just the dot products between the vector and the basis vectors. So let me write that down like more as a formula. But that's kind of like the cool fact about the orthonormal basis, that it just gives you like a very straightforward formula for these coefficients. The formula is I did it kind of in this case with 3 vectors just to try to make some sort of picture. But if you had like k vectors, if V1, V2, V3 up to Vk are an orthonormal basis, orthonormal basis of B, then any other vector V of the vector space is a linear combination of these meaning that V is like, let me put it like this, C1, V1 plus V2, V2 plus CK, VK. And the point is that there is a formula for each of these coefficients. Each of these coefficients is just the dot product between V and Vi. And here I is like 1, 2, 3, up to K. I mean, like the formula, it's kind of better to, it is better to think about it like in when you know the number of basis vectors, like in like how I did it before, where K, K was 3. But it's just like it's always the same. You just start with like you kind of just take like a succession of dot products, a sequence of dot products between the basis vectors and the vectors that you care about. I mean, I don't know if you remember like the dot product. It doesn't matter in which order you write the dot product, so you can also write that as Vi dot B. So it's just, I mean, the dot product A dot U dot B is the same as B dot U. So that doesn't matter. The important thing is that, if you want the fourth coefficient, you have to take the dot product between the fourth basis vector and the vector B. So let me show you this with an example, just to make it more concrete, because this example is one that I will use in a bit also for like the main application that I had in mind. Let me show you an example of how this works. Let's say V was this vector space XYZ, where X plus Y minus Z equals 0. Okay? So you should know by now how to find a basis, right? Like, so the question could have been first, like, let's find an orthonormal basis for V. Orthonormal basis for V. So how could you do that? I mean, like in this one is kind of simple because you can just use the equation to solve for z. So you can say that z equals x plus y, right? So a vector v would be like, x, y, z, but z is now x plus y. So this is like what? X times 1, 0, 1 plus y times 0, 1, 1, right? So this is a basis, right? This is a basis. But is it orthogonal? But they're dot product, right? But they're not. It's not an orthogonal basis, right? How do I know that it is not orthogonal? Because again, if I do the dot product between these two vectors, I get 1, which is not 0, right? So to get an orthogonal basis, a perpendicular basis, you need the dot products to be 0. So we cannot use this, like, to find an orthonormal basis, we cannot use this basis directly, okay? So how can you find the orthogonal? First, let's find the orthogonal basis using Gram-Schmidt. So, okay, yeah, in fact, this is actually the example. Oh, good, perfect. So if the matrix A for Gram-Schmidt would have been 1, 0, 1, and then 0, 1, 1. But this is a matrix. Let's see. Good, I'm glad I had it before. Let's see. Yes. But this is a matrix 1, 0, 1, 0, 1, 1. They're essentially the same vectors that we had found earlier. So they're basically these vectors. And so we already had found like an orthogonal basis and an orthonormal basis from before. So that's good. Let me just write it down here. So this is an example from before. So from before, we had found in fact, like we don't even need the matrix because we had like done that before. So from before, we had found the orthonormal basis to be let me copy paste it. So it was these two vectors. So now let's call these we can call these V1 and V2. Okay, and now so now we have the orthonormal basis, and then comes up the application of this formula I just gave you. So here's part 2. Let's say I give you the vector V, which is so this vector V is in the vector space because it satisfies the conditions for being inside the vector space, which is that if you add the first two entries and subtract the third one, you get 0. So 1 plus 1 minus 2 equals 0. So V is in the vector space. So now the question would be, write this vector as a linear combination of the orthonormal bases, right? So write V as a linear combination of V1 and V2. And so again, the idea is that V is like C1 V1 plus C2 V2, where what are like C1 and C2? C1 is the dot product between V and V1. So it's a dot product between 1, 1, 2 and V1, which is 1 over root of 2, 0, 1 over root of 2. And this is just what is this dot product? It gives you 1 over root of 2 plus 0 plus 2 over root of 2. So this just gives you 3 over root of 2. What is the second coefficient? The second coefficient would be the dot product between V and V2, which is 1, 1, 1, sorry, 1, 1, 2 dot the second basis vector, which is, okay, this one is a little bit more annoying. Minus 1/2 root of 0.5, 1 over root of 0.5, and the other one is 1 over 2 root of 0.5. So this one gives you minus 1 over 2 root of 0.5 plus 1 over root of 0.5. Yeah, I mean, oops. Plus 2 over 2 root of 0.5. I mean, sorry, I could just cancel these two, so you get 1. Okay, so this one, these two cancel out, right? Oh no, they're the same, so they, right. So what do we get here? You get so it's 3/2 root of 0.5. Which is, I mean, it's 1.5 over root of 0.5, if you prefer. I mean, now at this point, I'm just simplifying things, but this gives you root of 0.5. Yeah, I think this is actually better. It looks a lot better this way. So the second coefficient is root of 0.5. So what the claim that I'm making is that V, which was 1, 1, 2, would be C1 times the first vector. C1 is 3 over root of 2. So C1 times the first vector, but C1 is 3 over root of 2 times the first vector. The first vector was 1 over root of 2, 0, 1 over root of 2. Plus C2 times the second vector. And C2 is root of 1.5 times the second vector, which is what is the second vector? It was this mess. Minus 1 over 2 root of 1.5, 1 over root of 1.5. And 2 over root of 1.5. So like what I'm saying is that if you were to, do this combination, you will find 1, 1, 2. Not that, I mean, you don't need to check it or anything. I'm just saying like how it looks like in this particular case. So this linear combination does give you like, you know, if you rescale the first basis vector by 3 over root of 2 and the second one by root of 1.5, and then add them together, you will find 1, 1, 2. Okay. But I mean, and so that's okay, but it is a warm up for what I want to do in a second, which is apply this in to find like this projection matrix. So that's like, I'm about to show you how to do that, but let me see if there are any questions up to this point. Is that okay? So far so good. Okay, so here, this is the main application that I want to use all of this for, which is to find the projection matrix. Okay, and let me see how to explain this. So let's just continue in this example as a motivation, and then I'll give you a formula. So I don't know if you remember, you know, what this V looks like. This V, this equation, I had mentioned that before, it's the equation of a plane in 3 dimensions. Okay, so let's just, let me see if I can draw it. So let's go back, let's continue talking about this example. X, Y, Z, where X plus Y minus Z equals 0. That actually looks like a plane. So you can draw a plane. Oops, like this doesn't look so good, so. I think it would look better if I draw the X, Y, Z axis. This is V, that's how it looks like. Okay, but of course, not every vector, I mean, not every vector with 3 entries belongs to this plane. So for example, let's, like, I need to check, I need to use like a good notation, but let's see. For example, you know, let's take a vector, let's make this concrete. Let's take this vector U, which I'll put to be, let's see. Let's just say it's 1, 1, 1. Let me put like some, make this on GeoGebra so that you can see how this starts to look. Yeah, so let me show you this in GeoGebra so that you can see it. So what I'm saying is that you have this plane like X plus Y minus Z equals 0. That's the plane I'm talking about, okay? And then you have a vector that's not on the plane, like for example, 1, 1, 1, 1. Okay, let's do it maybe a bit bigger. Yeah, just so that it's more clear what's going on. Okay, so if you look at the vector U, which I'm calling 1, 1, 1, I'm going to put it in red just to use the same colors as the that I'm putting on my tablet. if you look at this vector u, right? This vector u is clearly not in the plane, right? So this is a vector outside the plane. And now what we're going to try to find, like here is like the thing that can be a little bit tricky. Just imagine that like you can rotate your head around. Let's see if I can. This rotation is making me dizzy. I mean, yeah, I think that if I try to rotate it, it's much more confusing. Imagine that you put like a light, a flashlight, or like the sun somewhere, and then you could like so that the rays of the sun are perpendicular to the plane. So what is going to happen is that this vector will make a shadow on the plane. Okay, and that shadow is going to be called the projection. So let me write that down on the iPad. It's actually easier to draw it on the iPad. So what I'm trying to say is that this vector u, right, which was, what did I say, 111? Sorry, 114. This was a vector 114. 114. This one is not in V, right? But it does have like some sort of shadow along V. So think of this as like a shadow. It even looks a little bit better like this. So like you have like the sun, here's the sun or whatever. You just have to imagine that the rays kind of come this way, so that you know, like it's kind of like a like the rays like move in this direction, so that like it hits like perpendicularly like the plane. So it will like there will be a shadow of this vector on the plane. So there's like this shadow, like a shadow vector. And this vector, I mean, this shadow vector will be called the projection. So this shadow vector is what you call the projection. It's called the projection of U onto the vector space V. And that's written as this way, projection of U onto the vector space V. Is that making sense? So that is what the shadow vector is. So again, like the point is that the shadow vector belongs belongs to the vector space V. So this by definition will belong to the vector space V. The reason what makes this like what makes this a projection vector is that there will be like a 90-degree angle here. Okay, so the condition for finding this projection vector, the key defining property is that if you subtract from what is this blue vector? This blue vector is actually, it takes a little bit of vector geometry to do that, but I mean, basically, like the idea is that the purple one plus the blue one needs to add up to, let's call this vector W. So the idea is like the shadow vector, which I'm calling the projection, when you add up this vector W, that should give you back the vector U. Maybe it's easy to see from the picture. This one plus this one should give you back U. And that's kind of like the parallelogram law for adding vectors. So W, W is going to be U minus the projection. So what you want, like the idea of like the orthogonal projection, I mean, this is also why it's called like this is sometimes called an orthogonal projection. The idea is that these vectors should be perpendicular to the vector space V. So that's why there's like a 90-degree angle here. Is perpendicular to V. Meaning that if you take the dot product between W and any vector on V, that should be 0. So W dotted with any vector on V should be 0. But what is W? What is W? W is this thing. It's U minus the projection. I'm about to give you like the formula, so but I think it's like a nice relation to do. So these, oops, let me zoom out. So D should be 0. But again, because this distributes, that means that U dot V, so U dot V is going to be the same dot minus, it has the same dot product as the projection with V. So it is the same as projection of U dot V. In other words, like this projection vector has a property that its dot products, the dot products between the projection and any vector on V is the same as the dot product between U and any vector on V. Okay. Why is that form? Okay, this looks a little bit weird. So why is this useful? Okay, why is it useful? Because that way you can actually give a formula for the projection. So here's like the formula. Like the formula is that this vector belongs to the vector space V. So it is a linear combination of the basis vectors, okay? But if you remember, if you're working with an orthonormal basis, then every of these vectors is like the dot product between the the vector that you care about and the basis vector. So it is just like just to write it down explicitly, it's like it is a dot product between the projection of u dot v1 plus the projection of u dot vk that times vk. Okay, this looks a little bit messy, so let me rewrite it so that I have a little bit more space. Projection of u one plus projection of u dot vk times vk. Okay, now that doesn't look too useful because like you don't know what this projection vector is, you don't know what the shadow is, but because of the defining property of this shadow, these dot products are the same as if you had just put u dot v. So the formula for here's like the formula for the projection matrix that or like the projection vector that you have to remember, and I'll show you how to use it now. What the formula that actually is useful is very simple. It's like the point is that you can replace this projection here with u when taking the dot product. So you can just put like u dot v1 times v1 plus u dot vk times vk. Okay, so this is the formula that is important. Like so like to find the projection, basically to find the projection, it is here v1, v2 up to vk are like an orthonormal basis of v. So to find the projection of a vector, the shadow, you basically kind of use the same formula that I gave you here, but only using the basis vectors for v. I mean, so it's essentially the same stuff that we have been doing before. So it's kind of because of these property that the projection has that its dot products are the same to the dot products that v would have with you would have with a vector in v. So let me let me do this more concretely because it can be a little bit difficult to see just from the formula. So let's apply this to u, which was let's apply this to okay. So what this formula is saying is that the projection of u, like the shadow of u, is the dot product between u and v1. What is v1 in this case? v1 is v1 was 1 over root of 2, 0, 1 over root of 2. We had found this before. This is the plane we have been using all the time. So it is 1 over root of 2, 0, 1 over root of 2. Okay, so that's the first entry. Sorry, this is the first summand, and the second summand is plus the dot product between u and by the way, this formula I will give it to you on the final exam. If so, you don't have to memorize it. You just have to know what everything means, like the V1 and V2 and so on, or like an orthonormal basis. But yeah, this formula, like I'll give this one to you. So and what was this other vector? Minus, okay, minus one, 2. Oops, this should be 1.5. And then 2 over, sorry, it was 1 over 2 root, 2 root point, 2 over root point 5. So it looks like a little bit of a mess, but it is not too bad because it just means it's a dot product times a vector, a dot product times a vector, and then you add those numbers together. So what is this giving us? So it's a lot better than what it looks like at the moment. So what is it? This dot product. Okay, this one goes away. So it's this with this. That's just 5 over root of 2. Let me put that with colors. 5 over root of 2. That's what you get when you do this dot product. And then times this vector. What's the other one? What happens when you do this this one instead? Yeah, let me write this as, otherwise it's just too annoying. Let me put this as 2 over 2 root of 1.5 so that I can just have the same denominators already. So when you do this dot product, you get this one gives you 4. This is 4 with 2, 6, and okay, so this is 5. Oh yeah, that's so much better. Okay, we're almost there. It looks bad, but it's because I haven't done the product. So when you multiply every entry by this coefficient, what does this give? Like you get 5 in the numerator, and then it's 5 halves, which is a lot better. So 5 halves, 0, 5 halves. That's the projection. And then, okay, let's see. Then the numerators will also be 5 in this one. So it's minus 5. What's this? Root of 0.5 times root of 0.5, that's just 1.5. So it's 1.5. Oh, okay, so over 6. And then this one gives you 5/3. And the last one gives you kind of similar, but it's with same with the opposite side is 5, 6. So just to add them together more easily, let me put the same common denominator. So this is 15 over 6, 15 over 6. So what this says is that the projection should be and I can also put this one as 10 over 6 if you want. So that everything looks more like the same. So that you get 10 over 6, and then 10 over 6, and then 20 over 6. So it's not that bad. The numbers despite the appearances. But the important thing is that the first thing to notice is that this actually belongs to the vector space, because if you remember the definition for the vector space is that if you add it, you see, the condition for being in the vector space is that if you add the first two entries and subtract the third one, you get 0. If you add these two entries and subtract the third one, you get 0. But more importantly, let's just check how that looks like on GeoGebra. That it is more illuminating to see how this looks here. So what I'm putting, let's call this projection W, is 10, 6, 10, 6 over 10, 6. Sorry, 26. And so you get this vector. I think I'm putting this on purple. Using purple here. So we can make it super thick also, so that it's easier to see. So I don't know how clear it is. Like, I don't know if you can see like the relation between the red one and the purple one, but it does look like, again, if you have like a laser, think that you have a laser that you're pointing perpendicular to the plane, that this tip would give like a shadow here. And what I'm saying is that the head, the shadow of the head is this point. That's kind of plausible. So it's cute. It's nice to see it. See it like that. So this gives you like the formula for finding the shadow of any vector you started with. Is that okay so far, so good? Okay, let me give you like finally the projection matrix. That's the last topic I wanted to cover for today. And as I said, like besides that, let me see if I can find the video. Let's see here. Yeah, so besides that, besides this topic, the only one left that I really wanted to cover is like, I don't know if you have noticed that I had told you that I have recorded my class last semester. So there's like this class about Connie sections, like the one that's called lecture 23. That's the only topic that I really want to finish for our course. It's relatively straightforward. I mean, if you want to just like, you can watch it over the weekend if you just want to know what all the material is for the course. Like you may need to watch a little bit earlier, like lecture, like you may need to watch a little bit of the previous lecture, but I mean, it's just like a quick application you see of diagonalization. So it is easier than what we're doing right now. But I'm just saying, if someone wants to go ahead, go into the future, if you watch 23 and part of 22, like that's all that's left. So it's only one more topic. So let me just yeah, but just to finish this thing up about the matrix, the projection stuff. Again, the idea of a projection. So what's the idea of like what is going to be the projection matrix? I still haven't told you that. So well, the idea is like you have like I don't want to do like a very specific picture. Like you have like a vector space. Like the best thing I can draw for a vector space is some sort of like a plane. You have a random vector u. Am I using the same colors? Okay, yeah, use u was in red. And then there was this projection, right, of u onto V. So the projection matrix it is a matrix that takes you to, so the projection matrix P of V is a matrix that takes u to the vector projection. Okay, so there's like going to be a matrix that will give you this shadow vector, and what's going to be the definition. And this is like also this is actually the formula I'll give you on the exam, like this one. Like the definition for this projection matrix is that the projection matrix of u onto V is just u dot v1. It is like a very easy formula. So I'll show you in a second how to use it. U dot v1 times v1 plus u dot v2 times v2 plus u dot vk times vk. This is the formula that you need to know where v1, v2 up to vk are like a basis for orthonormal basis for v. Okay, so it is it's a it is just computing these dot products that we have been talking about, and once you compute those dot products, you can extract the projection matrix. So let me show you that with an example which is a little bit faster than the one that I was doing. Here's like an example. Let's say that the vector space, like you'll see this is a lot easier than the one we were doing before. So the vector space is those vectors x, y, z, w, where x equals y and z equals w. Or let me put it like, x minus y equals 0 and z minus w equals 0. So the condition for being x, y, z, w, where x equals y and z equals w. So the condition for being in this vector space is that the first two entries must be the same, and the second two entries and the last two entries must be the same. So first two must agree, second two must agree. So what is the basis for V? This is easy to find. It's just like you write x, y, z, w as x, z, z, right? Because like the first two are the same, so they must be x, and the last two are the same, so they must be z. So this is just x 1 1 0 0 plus z 0 0 1 1. Okay, so the basis the basis is just these two vectors, right? They are already orthogonal. That's why I'm choosing this example, because it's like a very nice basis. They're already perpendicular, right? If you do the dot product between these two vectors, it's already zero, so there's no need to do Gram-Schmidt. So it's already orthogonal. But it's the only thing that we require to do is divide by their length. The length of each of these vectors is root of 2. So the orthonormal basis, like the orthonormal basis is 1 over root of 2, 1 over root of 2, 0, 0, and 0, 0, 1 over root of 2, 1 over root of 2. Okay. Is that making sense? So this is like the orthonormal basis. Orthonormal basis, or V. Okay, and now how you should think about this problem is that imagine that you have, like again, I cannot really make a very good picture because these vectors all have 4 entries, but you'll see what happens. So imagine that you have, you have V here. We have this orthonormal basis. So here you have V1 and here you have V2. That's like an orthonormal basis. And then you have this vector U, which you don't know what it is, so let's just call it X, Y, Z, W. Okay, so what is the projection, the shadow? Don't worry, like if you think about it, boom, 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 there will be a shadow that this vector makes somewhere in here. Okay, this is kind of maybe the projection. And the idea is that the projection, like the formula for the projection matrix is that the projection of U onto V is just going to be this projection vector. So it's going to be, if you remember like the formula for the projection vector, the shadow is the dot product between U and the basis vectors. So it's just doing U dot V1 plus U dot V2. There's only 2 basis vectors, so it's like a simple formula here. But what is this? What is U? U is X, Y, Z, W. What is V1? That's 1 over root of 2, 1 over root of 2, 0, 0, times 1 over root of 2, 1 over root of 2, 0, 0. So that's the first term. And then you're adding what is the second stuff is the dot product between U and V2 is X, Y, Z, W. 0, 0, 1 over root of 2, 1 over root of 2. And then 0, 0, 1 over root of 2, 1 over root of 2. Okay, so let me just to emphasize this, like let me put some colors in. So U is here, this is U, and then V1 is this one, right? Is here and here. And then the other one, V2, is here, here. Okay, but now, yeah, this is actually a lot faster to compute than the other one because like the numbers are way nicer. So when you do this dot product, you get like the first dot product, you get X plus Y over root of 2. Okay, times 1 over root of 2, 1 over root of 2, 0, 0. And the other one gives you Z plus W over root of 2 times 0, 0, 1 over root of 2, 1 over root of 2. Okay. So what is that giving you? I mean, if you do the multiplication, you get x plus y over 2, x plus y over 2, 0, 0, plus 0, 0, c plus w over 2, c plus w over 2. That's what you get when you do the multiplications. And then what do you get here? You get, if you add them together, you get x plus y over 2, x plus y over 2, z plus w over 2, c plus w over 2. And so I don't know if you remember, a long time ago, we saw how to find like the matrix that would take a vector to a given vector. So this is a matrix. There's a matrix that is taking this vector, u was called x, y, z, w. So there's this matrix that is taking this vector to this vector. How could you extract the matrix? It was literally just a coefficients, right? So the matrix was what is PV? The projection matrix in this case is 1/2, 1/2, 0, 0, 1/2, 1/2, 0, 0, 0, 0, 1/2, 1/2, and 0, 0, 1/2, 1/2. Okay, so that is a projection matrix. It's just a coefficient of the formula. Is that making sense? What's more useful, what is actually more useful here is to think about the formula itself, right? Like it's more philosophical. Let's just think about what this formula is saying. If you think about the vector, what is the condition for being inside this vector? The condition for being inside this vector is that these two entries should be the same, right? And that these two entries should be the same. So the condition for for being inside this vector space is that to have agreement between the first two and the last two entries. Okay. What this is doing, what this is trying to do is like, well, you started with a random vector, right? Like their entries may not agree. So the matrix is kind of smart to like this matrix is trying to force you to be inside the vector space. So the way in which it's forcing you to be inside the vector space is by saying, well, since I don't know what these two entries are, let me average them out, right? So this is like an average of x and y. And this one is an average of z and w, right? So what the matrix is saying is like, well, let me just average the first two entries. Once you do that and you place them as the new entries, then these two are by definition the same. I mean, it's just like the average. They're essentially the same formula. And this now the matrix is saying, well, since I don't know what they are, like the most like democratic thing to do is to average these two out and use those as the new entries for the shadow. So the shadow is kind of like an average of the first two entries and the average of the last two entries. And that will automatically be inside the vector space. So the projection is kind of smart in the sense that, it kind of tries to find like the vector that belongs to the vector space. Like the shadow is kind of like optimal in a sense because it's like the ideal way to, like if you have a vector, there will be many crazy things you could try to do to that vector to make it belong to the vector space that you care about, like find its shadow. But this projection is kind of like the most subtle way to find, like, to force it to be inside a vector space. So the projection formula, it is always, in a sense, it is the optimal solution. Like it can actually be, that can be proven using calculus. Basically the projection has a property that this length is kind of as little as possible, and that's why so actually you can, like, if you have taken calculus, you can kind of like find the distance. Like what I'm saying is like you can find the distance from this vector to this vector space, and the projection is like the one where this distance is the smallest possible. So it's like it's like an optimization problem. And in fact, that's kind of why this is used for the least squares method, if you have ever heard about it, because in the least squares method, you have like some sort of data that you measured and you're trying to find like a curve that fits this data. So the problem is because the data has some errors, like you may not expect the curve to match perfectly to the data. So you kind of have to find like a curve that approaches the best your data, and that can be set up as in terms of like a vector space problem. And the solution to the least squares method ends up being like a projection, using like a projection matrix. I mean, I won't like that's in the book, but I'm not covering that. But it's like an interesting application of least squares method. I mean, this is basically can be used for the least squares method. So, but I won't. Yeah, maybe just to finish now, to finish this up, let me just tell you two properties that are interesting about these projection matrices. The first one is that they're square. If you take a projection matrix and square it, that just gives you the same projection matrix. So one way to think about this is that the shadow of a shadow is just the shadow. Right, because like the projection matrix, what it's trying to do is find your shadow. Once you found your shadow, if the shadow of the shadow will still be the shadow. Like there's no other fixing that needs to be done. So it is like a fun exercise. For example, square this matrix, and you'll see you find the same matrix again. That's kind of fun. Like, I mean, you know, with numbers, like x squared equals x when x equals like basically 1 or 0. So you kind of need matrices for that to be kind of like an interesting result. So every projection matrix squares to itself, and the other property about the projection matrix is that the it is symmetric. And I'll tell you more about symmetric matrices next time. But its transpose is itself. It's its own transpose. Um, so basically, yeah, one of the things that once you know something like this, you know, these will like maybe I mean it's not too important, but this condition actually will force the eigenvalues of the projection matrix to be either 1 or 0. This means that the eigenvalues will be are 1 or 0, are 1 and 0. And usually, if you have like looked at computer science or like a basic course in discrete math or logic, usually the 1 is used as a truth value, like for something being true, and 0 is usually used for something being false, or like this is kind of like binary code. So this is like you can think of 1 as being true, and 0 as being false. So you can actually use these matrices to represent like outcomes of experiments that have only two possibilities. So the experiment could be like is the light on or off? That's either yes or no. I meant so instead of true or false, I mean yes or no. So yeah, so you can you could represent like certain like if the certain experiments only have two possibilities, then you can represent that by there are occasions where you can represent that by a projection matrix, where like the eigenvalue 1 represents the situations where you get like a yes answer, the eigenvalue 0, where you get like a no answer. And you can actually use that to hook up like these truth tables. I don't know if you have someone has ever seen like the truth tables for in logic for like and or not or so there's like it is all related, but I mean it's of course it's not something that we're going to do, but it's interesting that this can be connected to these like what sometimes is called Boolean calculus or like propositional calculus of like yes and no answers and things like that. But yeah, for me, like the thing that I really care about that you need to know is how to find the projection matrix. That's kind of like the question that I'll ask you. I'll give you a vector space and I'll ask you find the projection matrix onto that vector space. So you have to find a base, an orthonormal basis. And once you have like the orthonormal basis, you do something like this and then you're done. You'll see, I mean, there are a couple more examples like, yeah, like again on Tuesday, once we can do more examples if you want. It is more or less always the same. Sometimes the arithmetic can get a little bit tricky, but besides that, there's nothing really too mysterious going on. You can check like the practice exams I send you. There's like a couple of other formulas, other questions about finding projection matrices. So you can check those as well. But yeah, we can do more examples on Tuesday or depending on what you want to do. So as I said, yeah. So on Monday I'll just need some short, like some amount of time to tell you this application of to conic sections, and that will be the last topic for the course. So just like how to identify conic sections, which is like a fun problem, and it's a like unusual, like unexpected application of linear algebra, I think. So it's like a good place to wrap it up. So yeah, but like now, like it's essentially like everything except one question. The final, you like 90% of the questions on the final, you like you already know how to do with the material we have been we already covered, because there will be definitely one question about conic sections, but that would be only one. So everything else, like you can kind of practice like any problem that's not about conic sections. You can practice now. You should be able to do it. So yeah, I'll see you next time. If that sounds good.
Thank you, Professor. Have a nice day.
Yeah, you too. You too. Bye bye. Also, if someone wants to ask me something, I don't know.